Hello again everyone, this is Dr. Christopher White and let's get going again with earthquakes. So let's think about the different types of seismic waves now. Now I've already discussed that seismic waves will move either across the surface of the earth or they'll move through the interior of the earth. Now this gives us a very simple way of splitting up seismic waves. There are surface waves that move across the surface and body waves that move underground. So nice and straightforward. So obviously over here we have our surface waves and here we have our body waves. Now in terms of surface waves, the first type of surface wave is going to cause essentially the vertical surface to compress materials, whilst the other type of surface wave is going to cause the horizontal surface wave, so it's going to shear materials. So we have a vertical surface wave and a horizontal surface wave. So it's going to, one of them will cause stuff to go up and down, while the other one will cause stuff to go from side to side. Now, these are the waves which are actually going to cause the damage during an earthquake, because they're the ones that move across the surface, so they are the ones that are going to interact with things like buildings. Now, in terms of body waves, we have the primary body wave, also called the P wave, and this is a compressional wave, and it's the fastest of all the waves. Then we have the secondary body wave, which is called the S wave, and this shears material. So once again, it makes the material go up and down. Now these, as I say, are body waves, so they're happening in the Earth's interior. Okay, so surface waves, as discussed, they move across the Earth's interior. They will obviously cause the greatest destruction. Surface waves move across the Earth's exterior, the surface. They'll cause the greatest destruction because, of course, those are the ones that actually interact with things like buildings, and they are the slowest. Body waves are split into two types: primary or P waves, or secondary waves or S waves. So the P waves are compressional, and they can travel through solids, liquids, and even gases. Secondary waves, on the other hand, are incapable of travelling through anything but solids, and we'll discuss why that is in a second. So an S wave cannot travel through a liquid. P waves are around 1.7 times faster than S waves. So when we look at a seismogram of an earthquake, we'll see the P waves arrive first, followed by the S waves, and then finally the surface waves arrive. Okay, so this diagram is essentially showing you the surface waves. So surface waves come in two varieties. We have Q waves, also referred to as love waves. They're going to make the ground move from side to side. And then we have Rayleigh waves. They're going to make the ground move up and down. And there's a couple of links to videos here which I would recommend you take a second to look at, because they are genuinely quite interesting. So what about the body waves, the P waves and the S waves? Okay, well, sorry, just having a look over here for just a second. Do apologise. Just checking one thing. Okay, so what about P waves? Well, P waves are a compressional wave. So they are going to move through a material and they're going to compress it and then let it expand back to its original shape. Okay. Now they're going to travel quickly. So all they're going to do is they're going to literally push one atom towards the next atom, and then this atom's going to move back. But as this atom moves towards this atom, it's naturally going to push this atom away due to repulsion. This atom will then snap back to its original location. So as one atom comes in, pushes the other atom away, then this atom here goes back to where it started. So the best analogy I can come up with this is, imagine you had a room and you fill it full of, I don't know, say 2,000 people. And you get those people to, line up in lines of 100, one behind the other. Okay? So then what's going to happen is you are then going to have let's say a football player, let's say JJ Watt, or any other defensive end you fancy, essentially starting at the end of a long corridor, and that long corridor is going to end in the first row of people. So JJ Watt comes hurtling down the first corridor, he's moving at maximum speed, and he hits the first row of people. Well, what's going to happen to that first row of people? Well, they're going to fall backwards, and they're going to hit the second row. The second row hits the third row. The third row hits the fourth row. So the compressional wave, the impact from your football player, is being passed backwards, isn't it, through the rows. Now, the first row is then going to stand up and go back to their original position. Then the second row, then the third row. So essentially, as the pressure wave moves through, the waves are, essentially the rows are pushed backwards, and then they return to their original position. But in the process of being pushed backwards, they pass the energy on to the next row. And that's what's happening in our material. As one atom gets pushed backwards, it passes the energy on to the next atom. Done. So P waves will travel very, very efficiently through solid material, but of course they can also travel through liquids and gases. So let's think of liquids, let's think of water. Once the P wave hits the water, it pushes one water molecule towards the next, then it pushes that water molecule towards another water molecule. So once again, the compressional wave can move through liquids. In theory, it can also move through gases. Doesn't do it very well, but it can also move through gases by pushing one, let's say, molecule of oxygen towards the next molecule of oxygen, and then that molecule of oxygen will then get pushed away to essentially interact with another molecule of oxygen. So P waves move fastest through solids, slower through liquids, and slowest through gases. What about S waves? Well, S waves essentially make material go up and down. Okay? Now, that essentially they travel in a sideways motion. Now, because they're making material go up and down, it means the atoms must be linked together to allow an S wave to pass through. So this means S waves can only pass through solids because solid materials have essentially a crystal lattice. If there's no crystal lattice, so no bonds between the atoms, then that means the S wave cannot travel through. Okay, so once again, if it's going through a solid, that's fine, there are bonds. As soon as it hits a liquid, well, unfortunately, that's it for the S wave, it's done. Okay, so S waves cannot travel through liquids, and that's very, very important to remember. So we've already discussed this. P waves, S waves. P waves compressional, and S waves essentially are P waves are S waves. Sorry, what I'm looking for. S waves are sideways waves. Now, obviously, the most important thing is an S wave must have a link between atoms. If there's no link between atoms, the wave cannot continue moving forward. Okay. Whereas as a compressional wave, a P wave has the capacity to essentially just keep going through solids, liquids, and even gases. Okay, so how are geologists actually going to measure these waves as they pass through? Well, the first way we do it is through the basic seismograph, or also referred to as a seismometer. And this is the basic thing. This is what we've seen in the movies. So you have you have a pendulum, you have a metal ball at the bottom attached to a spring, and at the end of the metal ball there is a pen, and there is a drum with paper on it constantly rotating. Now, as a seismic wave passes through, the seismograph, which is of course attached to the ground so it can essentially sense the seismic waves will cause the pendulum to swing, and of course that will then be seen as lines being drawn on this reel of paper. More modern seismographs are essentially within these steel containers, and they have a solar cell for power supply. They'll have an antenna to actually relay the information straight to the lab. And these seismographs are a little bit more advanced. So some of them will actually be pistons, which will rise and fall as the pressure wave comes through. And that information will then be relayed to the to the center, so to the HQ, and some of them are still quite simplistic like this and require the swing of a pendulum to measure the passage of the seismic waves. So there's a couple of different types that are used in modern seismometers. So it doesn't matter which type you use, they're both going to produce this, which is of course our seismogram. And you can quite clearly see this is the background here, and this is obviously the earthquake hitting, and these are all the shocks that follow on. I'm very sorry, I've got to have a quick drink of water. So when we look at a seismogram, it typically splits into several distinct parts. Now here at the start we have what's referred to as the background. Now this is just the normal everyday seismic waves that are passing through an area. Okay, now these waves can be produced through things like people walking, cars driving along, that kind of thing. So this is just the normal background. Now when an earthquake hits, the P waves will arrive first. So we're going to see a sudden increase in amplitude of the waves. Okay, and as the P waves go through, initially we'll see the highest amplitude, then the amplitude will get smaller. Then all of a sudden, bang, the S waves arrive. We'll see another increase in amplitude. And once again, the amplitude will steadily decrease. And then, bang, the surface waves arrive. Okay, so we can essentially split our seismogram into 4 separate parts. The background, the P wave, the S wave, and the surface waves. Now obviously, the further away you are from the earthquake itself, the smaller the surface wave contingent will be. So if the earthquake is happening in the United States and you're detecting it at a station somewhere in China, well clearly you're not really going to get any surface wave activity. Now the time between the first arrival of the P wave and first arrival of the S wave is going to be very, very important to us later on. Okay, so obviously, as we've discussed, we have to, there's obviously the background, there's the arrival of the first P wave, so amplitude goes up and then steadily dies back down. Then the first S wave, amplitude goes up again and then steadily decreases, and then the surface waves arrive. So the P waves equals primary wave, arrives first, S wave equals secondary wave, arrives second. Okay, now obviously the further you are from the earthquake, the bigger the gap between the first arrival of the P wave and the first arrival of the S wave. So as you get further and further away from the earthquake, the gap between the first P wave arriving and the first S wave arriving becomes larger. So remember, the P waves are moving around 1.7 times faster than the S waves. So imagine you have a driving competition, okay, where one car is driving 1.7 times faster than the other car. Well, steadily over time, that car is going to get steadily further and further and further ahead, isn't it? So the bigger the distance between the epicenter of the earthquake and the monitoring station, the bigger the gap between the P and the S waves. And that's going to be helpful later when we try and work out, when we use that as a technique to work out the distance essentially for an earthquake. Okay, so here we go. So here we have 3 monitoring stations. Sorry guys. ISCO, DUG, and WUAZ. Those are our 3 monitoring stations. So they're going to record the seismic waves from an earthquake. So here we go. So these are our seismograms. So we can see WUAZ, the first P wave arrives here, the first S wave arrives here, and that's a gap of 73 seconds. Okay, then we have DUG. The first P wave arrives here, the first S wave arrives here. That's a gap of 57 seconds. And then finally we have ISCO down here. First P wave arrives here. First S wave arrives here. That's a gap of 14 seconds. So just based on this, we can see that ISCO is the closest monitoring station to the earthquake because the gap between the first P wave and the first S wave is the smallest. Now what we can do is we can use this data to triangulate the location of our earthquake. So how are we going to do that? What we can do is we can use a graph like this. So if we look on this side, it has the PS interval. So the PS interval is the time between the first P wave arriving and the first S wave arriving. So it's this data here. First P wave arrives here. First S wave arrives here. Therefore, that is our PS interval. And then finally, on the y-axis here, we have distance in kilometers. So as long as we know the interval, we can essentially come up till we hit the line and then come across, and that will give us the distance in kilometers for each PS interval. So what we have here is we have 73 seconds, 57 seconds, and 14 seconds. So 14 seconds is going to be down here. So we're going to come up, going to come across, so around 100 kilometers. In terms of DUG, so 57 seconds, okay, that's going to be about here. I'm going to come up, hit the line, come across. We're going to give or take about 550 kilometers. And WUAZ, 73 seconds, so we're going to come up about here, going to hit the line, and that's going to be somewhere in the region of approximately 700 kilometers. So you can see just by using the PS interval, we can get a distance relatively quickly. So what we can do then is we can then draw the circles essentially around our monitoring stations. Now please bear in mind the value we just read off is going to be the radius of the circle, not the diameter. So in the case of WUAZ, so that has a PS interval of 73 seconds. So remember, we would come up around here until we hit the line here, then come across. So the radius is going to be about 700 kilometers. So from here to here is going to be 700 kilometers. From here to here is going to be 700. From here to here is going to be 700. From here to here will be 700. Now, why do we do a circle like this? Well, the thing is we know it's 700 kilometers, but we don't know in what direction. Is it 700 kilometers north, east, south, west? We don't know. And the same goes for each of these monitoring stations. Now, what the interesting thing we can do though is once we draw the circles, well, there's going to be a point where the circles all cross. And that is going to be the location of our earthquake. Now, in order to achieve this, in order to triangulate the position of our earthquake, we need a minimum of 3 stations. You can't do it with less. Okay, so you need a minimum of 3 stations to triangulate the location of your earthquake. So we now know right here, this is our epicenter of the earthquake. So once again, P wave arrives, S wave arrives. This is the time between this and this. That is our PS interval. Obviously then after the S waves, we have the arrival of the surface waves. And this is our travel time graph. So remember, all we're doing here is very simple. We have our PS interval, in this case in minutes rather than seconds. So a 5-minute interval. Essentially we come across here until we hit this line here. So this is the this is a standardized line drawn on the graph. This would be provided to you, so don't worry about it. You would come across, so a 5-minute interval, come across till you hit the line. Then in this case you come straight down. Okay, and the value would be what, 3,400 kilometers, give or take. So once again, using the graph is a very, very simple experience. Now once again, please remember, this is the radius, not the diameter. So don't forget that. And you would obviously scale your diagram correctly using any scale bars provided on a map. So once again, we're going to follow this process again. So here we have 3 different seismograms: monitoring station A, monitoring station B, monitoring station C. And we can see the PS interval here: 3 minutes, 8 minutes, 11 minutes. Okay, we would apply this data to a graph like this, and that will allow us to work out the distance to the epicenter. Once again, remember, that is a radius value, not a diameter. And so what's going to happen? Well, obviously you're going to plot your circles, and where the 3 circles overlap, that is going to be the location of your earthquake, or the epicenter. And we can see it right here. So here we have 3 circles all intersecting right here where the star is, and that's going to be the location of our earthquake. And here it is in very, very large scale. So you can have an earthquake happening in China, and it can be detected in India, Australia, and all the way over in Paris. And then we can use that information to triangulate the position of the earthquake. Okay, so the next thing we can do is we can measure the size of an earthquake. So we're going to measure the amplitude of the wave. Okay, that's going to be important to us. So the amplitude in this case is going to be the distance from here to here. Okay, from the bottom to the top in this instance. So when we measure the amplitude, we're going to measure the amplitude of the largest wave, just the largest one. So in this case, we can see, if we look at the diagram, this point here, this is going to be the largest wave, and we're going to come from here, we're going to measure distance from here all the way down to the bottom of the wave here. So what are we going to do with this information? Well, once we have the amplitude and we have the distance, well, we can then put it onto a graph like this. So for each of the earthquakes, we've already worked out the distance from the earthquake. Okay, we know that ISCO was the closest and WUAZ was the furthest, so we got this information from a graph like this. That was relatively simple. And then this information, the amplitude, was of course taken from this diagram here. Now, when we actually do a lab using this, you'll see there's actually a little conversion factor required, so it's not quite as simple as just measuring it on the graph, but nevertheless it's not that difficult. And so you get the distance, you get the amplitude, and so in the case of ISCO, the distance was about 70 kilometers. The amplitude, based on the seismogram, is about, 25 kilometers. And so you'll draw a line from there to there. Do the same for DUG and the same for WUAZ. And you'll notice that they all cross. And they cross at 4 magnitude. And so we would say that this earthquake had a magnitude of 4. And this is how we do it. It's really that straightforward. Okay, so when it comes to earthquakes, how do we predict them? Well, the prediction of earthquakes is something that geologists have been desperately trying to achieve, along with the prediction of volcanic eruptions. And so far, we have failed spectacularly. Yep, we're not even close. So how do we try and do it though? So here's our diagram, and we have one fault block here, one fault block here, and our fault is of course coming through there like that. So the first thing we can do is we can measure the offset of features and other evidence for past movement. So here we have a river which is coming down here, okay, and now we can see when the river hits the fault plane, we can see all of a sudden it kinks over here and then continues. Now what we can do as geologists is we can look at this river, we can say, right, how much has this river been moved laterally every time an earthquake has occurred? Now this gives us some idea of how much movement there is in each earthquake. Now remember, we can link that movement back to the seismic moment. So that gives us some idea of how big past earthquakes have been. We can also look at changes in topography, which is related back to fault movement. And we can also dig trenches to study the history of the fault rupture. So we can look at the fault itself, and we can look at how the fault is operating, and we can also gather evidence for essentially how often the fault has been moving. And so you can see this is a very simple trench right here. Okay, now this one is for a very, very small fault, but you can see here are our marker horizons. We've got a dark band here, which is just down here, and we have a lighter band here, which is right here. So you can see this is the down thrown blocks. This, of course, this is the footwall, this is the hanging wall, and you can see the fault plane right there. So what we're going to try and do is we're going to try and determine displacement by matching parts of the same rock unit on the opposite sides of the fault. So we can see the displacement right here. Okay, and we can look at that and we can say, right, how much has it been displaced each time? It's all about displacement, and that allows us to work out essentially the energy, the magnitude of the earthquakes that are occurring along this fault. So we can also study faults using satellites. So here we have a satellite image which is showing ground displacement essentially from repeat satellite measurement. So we can see in this instance these lines are showing us the amount of displacement, and these concentric bands represent crustal buckling caused by elastic deformation. So we can see this area is where stress is building up. So this is where the crust is starting to flex. Once again, going back to the ruler, we're pushing the ruler, and the ruler itself is beginning to store the elastic energy. Okay, it's warping and deforming in order to store that energy. The rocks in this region are doing exactly the same thing. They're warping in order to store the energy along the fault plane, and that essentially is where the fault is going to eventually move, causing the earthquake. So here we have a situation. So this is the Nepalese earthquake of April 25th, 2016. Now in this case, the epicenter was located over here to the west of the city of Kathmandu. So what happened? Well, the earthquake itself occurred over here, but the stresses produced by this earthquake, some of them were used to produce seismic waves, some of them were used to actually move the fault, but not all the stress is used when a fault moves. Some of that stress actually gets passed further down the fault. So what's happened now is, so this is where the earthquake actually occurred, but some of the stress got pushed down the fault, and it's now situated just to the north of Kathmandu, which of course is the largest city in Nepal. So what you have is you have a situation where you have a fault in this area, which is very heavily stressed, just to the north of a very, very major city. And so obviously that's not a good thing. I think we can agree on that. And so what we have here is the real making of a possible disaster. And so what we're seeing here with this concentric pattern is we're seeing the ground warping due to the buildup of stresses. And that's simply because the stresses that were over here have been passed down the fault, and now they're right here. Okay, so how do we assess the risk if we can't see the fault at the surface? Now this is very, very common. Most faults are hidden to us. So there's a few ways we can do it. So the first thing we can do is we can look at outcrops, and we can look at exposures of deep uplifted rock. So we can see pieces of rock that have been essentially incorporated into things like lava flows, and we can look at that rock and we say, right, do these rocks show any kind of information, any kind of hint of stresses? Now that's not typically the best way of doing it. There are often far more efficient ways. Now one of the more efficient ways are of course mines. It just so happens that a lot of mining takes place in areas which are tectonically quite complicated. So these mines are being essentially dug into areas of the world which contain numerous faults, and of course these faults will be intersected by the mines. So, as the level pushes laterally, it might intersect a fault as it goes along. These faults will obviously be marked by the geologists, and so you can see where the faults are located underground. Now, another thing we can do is we can drill. Now, drilling itself won't tell us that much about the fault, but what it can do is it can produce something like this. This is referred to as disking. So you'll notice the rock itself is broken up into lots and lots of disks. Now, this is a classic indicator of rocks under stress. Okay, we can also see that this area has lots of calcium carbonate cement in it, lots of calcium carbonate veins in it, which have filled in the spaces in between the disks. So this is also telling us that this fault is essentially a channel through which fluid is moving, and calcium carbonate is being deposited as the fluid moves through. So what this is telling us is, as we drill down, if the drill core is taken from here, it's telling us two things. Number one, we have a fault, and number two, that fault is under stress. So it has stress built up. So a fault that's not under stress, when you drill through it, you're not going to get disking. A fault that is under stress, when you drill through it and remove the core, you're going to see in the core disking, and that's telling you that fault is under stress and therefore a higher risk. So obviously we have the situation where we have magma bringing pieces of rock to the surface. Those pieces of rock can, in some cases, give us indications of the presence of faults. So certain types of rock, like tectonites, you might remember that, produced by fault movement. If they're, if tectonites are included within the rocks, then that tells us, right, there's a fault in the area. Now, there are also other ways we can look at the subsurface. So we can use geophysics. So we can use processes like seismic reflection data, also referred simply to as seismics. So seismic reflection essentially uses seismic waves, the things created by earthquakes, but in this case we're making them in a man-made style. We're making them by ourselves. So you can make them a few ways. The simplest way is you take a steel plate and you hit it very, very hard with a hammer, and that sends seismic waves into the ground. You can use specialized pieces of equipment, things like vibratrucks. That's essentially a truck that comes along and it has a big steel plate that drops down onto the ground, and then the truck essentially vibrates that steel plate, once again producing seismic waves. And the other, one of the other more efficient ways of doing it is simply digging a hole, filling it full of explosives, and then blowing up said explosives. Once again, that will produce lots of seismic waves that will go down into the earth. And the reflection of these seismic waves and their path back to the surface can be used by geophysicists to essentially image the subsurface. And so you can see in this particular instance, we have a situation where we have a large fault coming down here, like so. And we have a fault block dropping down along that fault. We also have another fault over here as well. And so this part of the fault block is dropping down more relative to this part, so we have rotation going on. We have a sequence of rocks which are dropping like so. And we can pick out individual layers, so we can see the movement, and we can also see the layers of rock. So we can work out very, very quickly, right, that's where our fault is. Now, seismic reflection data is super duper good. However, it's a bit pricey to collect, so that's a bit of a problem. Now, so there are also other methods that we can use, and these methods include electrical survey. So we can do things like electrical conductivity or induced polarization. So these are methods by which we try and pass electric currents through rocks. So some rocks will naturally be quite conductive, and the electric current will pass through them quite easily. That type of rock would therefore have a low resistance. Some rocks, on the other hand, are very unconductive or have a very low conductivity, and so they will resist the electric currents. They will have a high resistivity. There are also, there's the reverse situation, which is called conductivity, which is how easily does the rock conduct electricity. So you have conductivity, resistivity, magnetics, gravity, and you can use all of these different methods to look at what's happening underground. So here we have an electrical survey, in this case conductivity. And what can we see? Well, we can see that we have an area of low conductivity marked out here in blue. And then we have an area of higher conductivity and medium and very high conductivity marked out here in yellow and red. So that's telling us there's a different feature going on here. Now, once again, you can see this wedge shape, and you can see that wedge shape would match quite nicely with something like so. So we can guess straight away there's probably a fault right here. And that fault is moving with this being the footwall dropping down and this being the hanging wall. We can also use techniques like magnetic data. So obviously some rocks will naturally be quite magnetic, you know, for instance, if they contain large quantities of iron minerals, and so they're going to produce a magnetic high. Some rocks will, you know, be poor in magnetic minerals, and they'll produce a magnetic low. And so, for instance, if we look at this diagram here, what can we see? Well, over here we can see we have a magnetic high. That's granite. Okay, granite typically contains some iron minerals in very, very small amounts, but they are there. So that will typically give it a relatively high response. Whereas over here, we can see we have a buried river channel. So that's going to be filled with, you know, coarse clastic sediment, or, you know, so sands and gravels. And so that is going to have a relatively low magnetic signature. And so we can use magnetics to see things like river channels in the subsurface. Now, once again, going back to gravity. So gravity will actually vary across the surface of the Earth. So different rocks will essentially increase or decrease the gravitational field of the Earth. So we can see we have exactly the same situation that we have up here. We have an area where we have a relatively, we have a positive gravity, where we have positive gravity value. And we can see as we go this way, the gravity value steadily gets lower and it eventually becomes negative. And then it's coming back up on the other side. And that's because this area here is filled with clastic sediments. Clastic sediments will have a relatively low gravity signature. In contrast, this material here, so this material here marked out in blue-grey, that's probably going to be the basement. That's going to be made up of rocks like, you know, granites, other igneous rocks, maybe some metamorphic rocks. And so this is going to have a relatively high gravity signature. And so we can pick this out. We have an area with a high gravity signature here and a region with a low gravity signature here. And so that's suggesting that, right, there is something going on here. And if we look at the process data, we can see it would look something like this. And once again, we have this classic wedge shape. And if we refer back to the diagram here, we can see the fault is going to be on the back side of it. So we know there'd be a fault right there. So this is just using, you know, geophysics to image the subsurface. Okay, so this is going to be quite a good place to stop. So once again, get up, have a walk around, have a drink, have a snack maybe, and come back when you're ready for the next part.